So, of course, when you're presenting a talk, you're deep in the thought of what you might do, and around us is the news that things in Valencia are not that good, you know, and of course, when I was coming here, I was thinking that the flight is delayed, there's a rainstorm in Barcelona, I got on the plane at 8:30, didn't get out till 12:30 because of the storm in Barcelona, and all of a sudden, you know, you're looking at the headlines, and there's tragedy everywhere. Yeah, there's tragedy everywhere, and of course, what I say when I look at this is that the climate change that people are seeing seems to be getting a lot closer. You know, those things which we hardly noticed, all of a sudden, are right in front of you. Yeah, and then of course there are the pandemics, of course we know, resource depletion and overpopulation, digital threats. I change my password like twice a week now, yeah, because we've got digital threats. Yeah, and then of course economic instability, and then artificial intelligence, talked about today. Yeah, something for the good, but of course it doesn't always work for the good. So people like you have to keep a mind to these things. Yeah, and then of course I have to also apologize to two people, you know, one to my team, one to Enentia, who I gave this very talk to yesterday, so it's a bit of a repeat for them, you know, and of course thank also companies like Almac and Michael here and his group who have supported our company for many years before. You know, so I hope that this talk is a credit to the amount of effort they've put in my company. So founded 35 years ago, I started it pretty much straight from university. Our company became a developer for Shell and then for GSK in the pharmaceutical sector. We became a fully established service provider. We have a global customer base, and we have carried out about 1,000 installations. And we work for the biggest companies in the world. Yeah, all of them. We work for all of them. Yeah, if you say to me, what are we doing at the moment? So at the moment, we work for Formula One. Yeah, we work with the best companies. And then, of course, there are some companies here which are more prominent than others. And then, of course, we have to make sure that those that are not so prominent are also seen. So whenever you have a business, and I have many, yeah, you have to have an approach. What's this business do, right? So for our reactor business, which obviously started off in reactors, we've changed tune a little bit. Yeah, we now go for, you know, the cartoons like Steve produced. I thought we've got to do one. We go for high throughput experimentation because this helps to improve people's productivity. We go for continuous chemistry, again, because it's an improvement in productivity. And lastly, we do robotics. And of course, the last talk, I know all too well how complex that building instrumentation to work good robotics is. And of course, if you've been running for 35 years, you will have patents in the course of the development work that you do, and here is some of them. And we will have products which come from those patents, which you know, provide us with a revenue, and these are our principal products with one of the companies. And today I want to talk to you about the first two products where we've filed patents successfully granted, and quite different products, quite different challenges when we're dealing with that kind of product. And then at the end of the talk, you know, I don't have much time, but I want to talk about using one of our products for preparing polymorphs in a different way to the familiar ways that you already understand, and particularly focusing on the blue parts of this presentation: thermal activation of solid substrates, crystallization from the melt, and mechanochemical techniques. So we think we've got something there which no one else has, and we can talk about it and maybe open a forum later. So as I say, at the end of the presentation, you know, I will share with you this new method, and let's see how much appeal it has to the people who do those kind of experiments. So when we look at our patents, yeah, and if you look at ChatGPT, what are the things that you look for in a patent, right? It'll give you 30 things to look for. We only look for 4 things, yeah? We look whether or not our patent has a secure domain and branding. So one of the products, miniature check valves, we own miniaturecheckvalves.com. Yeah, and for a polar bear, we own polarbearplus.com. So our access to the internet is as sharp as it possibly can be. And the information that we portray on the internet is supposed to be of the highest quality. The second thing we look for is pricing strategy. Can someone afford to buy this product and for us still be able to afford the costs of securing a patent, you know, in the countries that we want to secure it in? So the costs of a patent, if you are going to secure in Europe and the US, will cost us £20,000. So will we sell enough of this product at least to make £20,000 to secure it in 2 countries? And is it going to be able to afford the marketing budget that we need for it, which will be at least 40% of the cost of the product? So if these numbers work, then you've got something. Yeah? And for the 2 products that I'm going to talk about today, they do work. A miniature check valve, a very simple product. You can see it allows flow in one direction. And you see this little thing there showing that when you've got liquid flowing through that tube, it flows in one direction and opposes the flow in the reverse direction. A very simple thing, right? And this product is particularly good because it only has 4 parts to it. Yeah? When this patent was granted, I cried, because a patent with only 4 parts is a miracle. Yeah? When you think about your robotic parts that we talked about earlier, I couldn't, you know, I wouldn't know where to start. You know, procedures, processes, and you don't need a lot to get past them, the more complicated they are. Yeah? So these 4 parts, the body, the seal, the spring, and the inner. 4 parts to make this non-return valve. And we have patents on this in Europe and in GB and in the US. We didn't follow the patent, Chris, we didn't follow the patent in the Middle East. We felt that there wasn't much of a market with small valves with big oil companies. Yeah, I mean, I did talk to them though, and they said, what do you want to make one of those for? Yeah, didn't quite get it. So what are the advantages of this commercial, you know, what are the commercial benefits of this valve? You can see, you know, the microscale feasibility, leak-proof, customized geometry, lightweight, high-end, a strong market potential, and very cost-effective. But of course, with every patent, there are the disadvantages. Yeah? So disadvantages are complex machining, perishable seal design, testing requirements for, you know, manufacturing and testing, and the sensitivity to the cracking pressure. So you see, all these things come into it when you think, are you actually going to make any money from this thing? Does this product make money? It does, right? Why does it make money? It makes money because there's no alternative to the smallest miniature check valve in the world. Yeah, so that's what we've got. We've got the smallest miniature check valve in the world. And if someone wants something small, he has to look at this thing, right? And our conversion rate for this is quite high. So this is just like as a side, 4 components in a patent. This patent is a little bit more complicated, right? And beautifully explained by Steve in its application, right? Here, you've got a device which I say to people who I meet at a party, I say, it's like a washer-dryer. You know, it does 2 things at the same time. This is like a fridge and a cooker combined. They get that. But then I go on to talk about this and they still don't get it. Something that cools down to minus 40 degrees and heats up to 150. No one in the world makes one which is self-sufficient, and the only thing you've got to do is plug it in. Only us. And thanks to people like Almac who support us when we're manufacturing things like this, we are allowed to pay all of the costs, sort out the patent costs, make sure that it's sold at a reasonable price, although I can tell you that many people think it's an unreasonable price. Yeah? And surely we find a way. But what are the unique selling points of this product, you see? So we say it's a device that replaces dry ice solvents and a device which replaces the oil circulator. Yeah? I saw a few oil circulators in the presentations earlier today. I wasn't very happy about that. But anyway, we move on with climate change and what have we. We have a device which is 10 times more energy efficient than any other comparable device. So if you bought a circulator and you were trying to get down to minus 40 degrees, I'd be paying attention, yeah, then you're going to need 10 times more power than what we use. Yeah? And then, of course, we have a device that we've designed so that you never lose your data. And then, of course, you know, just like James Bond wants to make the perfect martini, when we've got a heating device, when we've got a heating cooling device, everyone wants to talk about the stirring. You know, should it be shaken? Should it be stirred? Well, I wanted to make sure that every conceivable type of stirring that could be applied to this device, we've managed to put in. Yeah, from small scale down to 1 mil overhead stirring up to 1 litre. And then we've got these other options like ultrasonic mixing, and we've got this high shear homogenization, tumble stirring, you know, rather niche applications where you would have different kinds of mixing. And I felt that this product should have every conceivable form of mixing that you can have. I can say that because I'm the owner. Right? If someone else was saying it, they'd have to discuss it. So what are we trying to do? We're trying to replace this. We're trying to replace cryogenic consumables where you're trying to get dry ice, you know, which is a gas, which is CO2 compressed somewhere, delivered to your lab, you use it, the solid then sublimes to take the CO2 back into the atmosphere, and that costs money. You know, that costs money. And that's not really a very sustainable route for using something where you don't need to. Yeah. And then you go on to getting rid of these, you know, laboratory circulators. Only about a month ago, we have a system, a flow chemistry system, which requires a circulator, sadly, yeah, where we were using steam as the heating agent, wanted to change to a circulator, and the German government will not allow you to use oil in a circulator because it's harmful. So you've got to get a special I said, what about all these circulators they're making, right? So I would just say, just keep your ears open on the use of circulating oil as a safety part of the science that you do. You know, these circulators are not, the oils that you use are not as safe as you might, I mean, some are, and then some are not. So you have to be careful about what you're using. Yeah, and then we come to the patent itself, right? So the patent itself is, you've got a cooling coil, which is shown on the right in the schematic here, and then you've got the compressor, and numerous sensors going to a controller, a very sophisticated controller, a damned expensive controller. In heating only, if you want to make a controller for a device which heats only, it will cost you less than €1, yeah, in production. Yeah, if you're trying to get this thing to work, you know, it costs 1,000 times more. Yeah, but that's probably because we're not in production, if you see what I mean. It might cost less if we made more, but that's the name of the game. And where's the patent? The patent is the red box on the left-hand side. So if you then go to what is that exactly? You see it here, right? At the bottom, I don't think I've got a pointer, but at the bottom, you see you've got these cool heat sections which sit underneath the plate onto which you put your vials, you know, like on a hot plate. Yeah? And we're controlling the temperature and the power output for the heating and the cooling areas underneath the plate. So you can see the graph at the top. If you want cold temperatures, both working at the same time, you'll have more cooling power and less heating power. And if you want to go to hot temperatures, you'll have more heating power and less cooling power. We're no longer relying on convection. Yeah? We're controlling everything. And we're controlling the temperatures of the plates and of the heating side and of the cooling side. And ultimately, so we're controlling T1, T2, and T3. And it's your job to decide whether you want to control the temperature of T4 and T5. Yeah? I can honestly say to you, this is devilishly complicated to do. But it does work. When you look at the data of how good the control is for an object which is controlled on our polar bear, you see that the temperatures are almost perfect. And because we can control the level of heating and the cooling in such an accurate way, we can create all kinds of shapes in terms of profiles. You know, crystallization might need a different temperature profile from nucleation, for example, which might need a different, temperature profile for something, for example, if you were just cycling a material, continually crystallizing and dissolving it over successive cycles. All of these things are possible at a touch of a button, or perhaps even by the programming on a computer. So this is the most elaborate hot and cold plate you will ever buy. And the problem is, you have its advantages, many of which I've said: compact, efficient, unmatched temperature range to any other product that you'll find, huge number of accessories, a method of collecting data digitally, but it also has its disadvantages. Yeah, the disadvantages for exploitation: it's a higher cost. You're telling people to move away from an established method of which they work, which is this acetone dry ice thing, and they love doing that. Yeah, I could talk to them all day, and they will still go back to their lab the next day and do just what they've been doing. And then, of course, when you've got a new technology, it always takes time. Yeah, this business is good, but it just takes time. Yeah, every year you've got to meet 50 people, and you might sell, a few, and then every year you're going to meet another 50 people. But eventually, they'll all come aboard because the product is a good product. So now I come to this end of this talk where we talk about methods of making a polymorph. I've got a polar bear, so I can go down to temperatures down to -40 very easily just by pressing a button. And I've got this device here, which I came across, a couple of years ago, which is a homogenizer. Now, in your area, Michael, you use these, on a regular basis, right? But homogenization, whilst it gives you very uniform particle control, under the influence of a temperature-controlled polar bear, allows you to manage a crystallization. So the homogenizer, for those of you who are not familiar with it, offers a high level of shear to a solution, a slurry, into which you put the probe. It just looks like a probe. It's like a 12-millimeter thing. You drop it down into a 100-mil vessel, you turn it on, and it gives you the most aggressive high shear mixing you can imagine, right? If there's any particles in there, you'll destroy them down to a minimum size. So the thing about a homogenizer is, if you're using it, this shear generates quite a lot of localized heat, yeah? And such so that when you're using it, that you can feel the temperature of the area just around the homogenizer getting hot as you use it. So the experiment is this. You buy a polar bear, you put one of those things in it, right? You have a solution in your 100-mil vessel at -40 degrees, so it will be a slurry or a solution with a solid, and it'll be suspended in there, and it'll be stirring around, and then you turn on the homogenizer. And so what the homogenizer will do is it will warm up the solution very locally to where the rotor is, and at that point, the liquid, the solid will dissolve, because you'll get to the solution temperature. I see Stevie's looking at me very skeptically here, but you get to the temperature where the solid goes into solution, and immediately around the path where that particle is ejected, you've got a solution at -40 degrees. So you've applied that extreme temperature stress through the acting of this high shear, and your solid, I predict, would come out not with the same structure that it went in. And so my idea of how you produce a polymorph using our polar bear and some other conventional equipment is to tinker around with the speed of this homogenizer. So there's a calculation that will tell you what the shear rate is, because you've got a diameter, and you've got a gap, and then you've got a speed. So you can control the shear rate, and you can control the temperature, because the polar bear will do that for you, and you can manage essentially the stress that the solid sees in the course of it re-solidifying in that system. And then, of course, you can put thermocouples in to measure the temperature, and you can control the rate at which the thing is pulsing, because the homogenizer can be pulsed to run every second or every 5 seconds, or turned off altogether. And with the combination of a very cold temperature and the high shear that the homogenizer gives you, I think there's an opportunity in that stress environment to produce a polymorph. So I've only got 15 minutes, so I'm afraid what I can conclude by saying is, you know, there are different kinds of innovation. There's innovations which are very simple, 4 parts, which make miniature check valves, which, as I say to you, is of interest, because people who want to use the smallest check valve in the world want to put it in inkjet printers and want to put it in drones because of the lightness of their weight, or when they want leak-tight solutions because ours has got a seal. And then there is more complex things like our polar bear, which takes a lot of calculation and a lot of electronics and a lot of computer programming to make sure that the heating and cooling that you guys have asked for gives you the perfect control that you are looking for. And I hope that with that conclusion and with this effort, and thanks to people like Steve, who demonstrates it so beautifully well in the work that they do, and Victor, who I've always told him was mad to open a company when he's got 2 young children. You know, these things come through in the end, and all shown to be successful. Thank you.
Only time for a quick question, or if not, we can leave it for after the event. Anything quick? Anthony?
Just a comment, not really a question, but one thing you didn't mention is the big advantage of using these systems, a polar bear system, in a high-potent isolator, because it means you don't need to take in any ice, no oil, very space compact.
No ice, only power.
Exactly.
Only power. And a tenth of the power less than you would use for a circulator to get the same temperature.
And a very, very small footprint as well. So it's a really good device if you have a small
well, very compact, so it weighs 12 kilos and just a bit larger than a conventional hot plate.
So, we've got a couple in our labs if you want to come and see them working. Thank you very much, Bashir.
Pleasure.
Thank you.